In this video, we'll take a look at some linear regression basics. Really, this is just a crash course in the assumptions and some of the foundation of linear regression. We need to better understand the foundation of linear regression in order to take a look at other research papers, to read our own SPSS output if we're conducting a quantitative study and we have continuous level variables. So we've been talking about our relationships between independent, our x variable, and the y variable, our dependent or our outcome variable. Now, we know that correlation does not equal causation. And I've also said that it's highly likely that there are a number of influential measures that are kind of in play when we're taking a look at what's going on with our dependent or our outcome variable. Linear regression allows us to take into consideration all of those external factors, right? So if we have, say, we have a city and we're really trying to figure out within this city what is influencing crime, right? What is influencing crime? Or stated better, what influences changes in crime, right? We often want to know why it's going up or why it's going down. So we may begin to think that, well, there's things like, based on theory, there are things like economic indicators. There are laws and legal changes. There could be, let's see, what else could it be? It could be where the city is located, right? Whether it's urban or suburban, maybe rural. Could be changes in the population, right? You could have a lot of people move out, which makes crime look like it's going down. Or a lot of people moving in which case crime may be going up. It could be things like, it could be the changes in a population. It could be changes in something like population. We'll just say demographic, right? Maybe all of a sudden, after the COVID baby boom, 15 years from now, we have this boom of young males in a city and suddenly crime starts going up. Or we have a huge boom of young females and maybe crime stays the same, goes down. Who knows what's going to happen, right? Okay, so we're taking a look at this idea that an independent variable can affect a dependent variable. But we know that it's definitely more than one thing, right? In this case, we're going to be looking at something called multiple linear regression. Now, before you can do any type of regression, and there are several, before you can do any type of regression, you have to meet some basic assumptions. All right, so for multiple linear regression, let's just knock out some assumptions here real quick. The first is that the data are homoscedastic. Big word. Homoscedastic. We'll have a better idea of what that means in a moment, but basically what homoscedasticity means is that the errors in our prediction don't vary significantly between points. So our errors in our prediction don't vary significantly. We want them to be pretty right on, right? Okay, so we want our data, our prediction to be homoscedastic significantly. Okay. Next, we want to make sure that our observations are independent. Now, what that means is basically this. When I talked in the correlation video, I said that correlations range from a -1 to a +1. And if we have a correlation, a relationship that is statistically significant and substantively significant, you're looking at something greater than 0.95, 96, 98, you have to wonder if you have basically the same variable being measured twice, right? There's what we call autocorrelation. These two variables are so highly correlated, they may as well be the same thing. We don't want that. We need observations that are independent. They have to be their own thing. Our measures have to be on their own. Next, we want our data to really follow that normal curve. Makes it possible for us to plot our data points and be pretty confident in where things land. So a normal curve for multiple linear regression. If you have a different type of shape to your data, there's other types of regression we can use. Let's see. And last but not least, in a linear regression, we want a line to best represent our points in the data. Remember when in the correlation video, I showed you that sometimes you could have a curvilinear relationship. Multiple linear regression is going to fail you if you try to do multiple linear regression and you actually have a curvilinear relationship. So you absolutely want to make sure that the relationship A exists, or you should stop doing what you're doing. Nothing to look at here. And that it's linear. Now, it could be positive linear, it could be negative linear. It has to be linear. Okay, you have to have a relationship. It needs to be substantively and statistically significant correlation, and it needs to be linear. Okay, so now we have the assumptions. Let's say we meet all of those assumptions with our data. Let's think back to algebra. And no PTSD here. When we think back to algebra, we may remember the formula for a line, right? So you can write the equation of a line by finding its slope. And in algebra, we use letter M for slope, right? By knowing its y, the line's y-intercept, and you need an x value. Worst case, you use 0. So the equation for a line is y equals mx plus b. So what does that have to do with regression? Well, essentially, what we're doing in regression is this. We are taking plots. Here's a bunch of observations here, going straight through our equation of line. And we figure this is probably a, moderate, maybe a slightly weak correlation, positive, right? What we're doing with regression is we are saying, if we take a look at all of the variables we can, all of those different factors that we theoretically think have something to do with whatever our dependent variable is, we were using crime, that was our y, and we were using percent poverty, that was our x. We are saying, I think if I take into consideration all of those other factors that could go into changes in crime, then how well do my predicted values, and so your predicted values, well, I'm doing that with this yellow dot here, we'll call that y hat, predicted observations. So predicted values. How well does my predicted value do when I take a look at these observed values? How close am I? Right? That's what we're looking at. And how much error is acceptable? So the equation for our regression line, this is exciting, y hat equals mx plus b. Let me go ahead and give you the equation for m and the equation for b. And b, just remember, b is the y-intercept. Okay, here are the equations. So for m, we have our sample size times the sum of all xy minus sum of all x times the sum of all y divided by, well, that wasn't very nice of me, divided by sample size, sum of all x squared minus sum of all x squared. Should ring a bell after you've watched the correlation video, right? All right, and b, our y-intercept, is equal to y bar. It's super similar to x bar, right? You just take all of your y values and you divide them by n. It's your mean y value minus m times x bar. And we can write this in a different way. And the better, in most cases, the easier way is to do sum of all y divided by n minus m sum of all x divided by n. Stay tuned and we'll take a look at how we can predict values using linear regression, and then we'll figure out what multiple linear regression does, and we'll take a look at some SPSS output.